theory. Now, that's just an introduction. This is where it gets very important. Electromagnetic radiation, which is your whole start of chapter 6 in your textbook. So, what is electromagnetic radiation? The energy emitted due to electron movement. So when electrons move, when we have the movement of electrons, and you guys will learn this in Chem 2, when they're heated, when a sun or whatever, when you guys heat elements, electrons, the kinetic energy increases. You guys will learn about kinetic energy. Electrons begin to move. So when electrons move, the movement of electrons releases energy. And we found out that different energies of light correspond to different wavelengths. So when energies move, when atoms move, we see they have wavelength, they release energy. So wavelength corresponds to energy. And we're going to talk about that over here, based off what Planck proposed. Now, electromagnetic radiation is characterized by wavelength and frequency, and wavelength and frequency are related to speed. You guys are going to have to understand this for today's activity, but Hochschild loves to put this on a test. So, electromagnetic radiation, which is basically energy emitted due to electron movement, is characterized by wavelength and frequency are what? Related to speed. So this is the equation here. Am I on your way? Yeah. So the equation in green, you guys see that speed is equal to wavelength times frequency. And speed of light is a constant. And I wrote here, so this is speed, wavelength, frequency, and these are their symbols, units. For this test, it's really important because you guys are going to see on your activity, they're going to have wavelength in nanometers. You guys have to convert it to meters. He's going to do the same thing on the test. He's going to give you guys stuff in nanometers. You have to convert it to meters. And he may be a little tricky where the answers are the same, just different notations too. So because it's obviously multiple choice, you could understand it. You know Hochschild likes to trick you guys. He may make it, instead he may convert it where it's not nanometers, it may go to decameters or something like that. Understand that. So nanometers, which is 10 to the negative 9, you have to convert it to meters. And that's frequency. Now the speed of light is constant for all forms of electromagnetic radiation. Cool? So, and this is the constant, speed of light. 2.998 times 10 to the 8 meters per second. Again, meters is emphasized here. Cool? Okay, again, he may play around. Well, he won't do anything here, but wavelength tends to change. They tend to give it to you in nanometers. So just know that speed of light is constant when you're doing your equations. This is always given. You guys can also round it up to 3.00 times 10 to the 8, but the actual number is 2.998. Cool? Now, something that's important that you guys are going to see on your test and your activity is this whole electromagnetic spectrum. And you guys have to really understand this because he's not going to give this to you guys. So this is in your textbook. I just drew it out for you guys again. See, all the forms of electromagnetic spectrum, or all the form of electromagnetic waves. Again, what are electromagnetic waves or radiation? The energy emitted due to electron movement, when electrons move. Cool? And is related to wavelength. So we see here we have gamma rays, X-rays, UV light, visible light. Visible light is the only form of electromagnetic radiation that our eyes can see. That's why we can see red, yellow, green, purple, whatever. But we cannot see X-rays or gamma rays or IR or microwave. These also come in the form of light. We just cannot see it. We can only see visible light. Cool? And then we have the IR, microwaves, radio waves, long radio waves. Cool? And if you guys look at your spectrum, if you're going from the long radio waves, from the right to the left side, towards gamma rays and X-rays and UV light, energy increases. Reverse. As you're going from the gamma rays, X-rays, to the radio waves, microwave, and long radio waves, wavelength increases. So there's an inverse relationship. By the way, I'm in the process of typing up your third review sheet for the third test. It's already at 40 pages. But it's chapter 6, 7, and 8. If you guys understand that, you guys should get an A on your test. Yeah. I've been typing it up for you guys. It's a lot of stuff. So, yeah. So I just do like little by little. I do like spend like 2 hours a day on it because I have a life too. I have my own shit to do. But yeah. So I just wanted to let you guys know, like, don't think I forgot about you guys. I'm just trying to type up a review packet for you guys. So, cool? 3 chapters. So, but back to what I was saying. So if you go from right to left, energy increases. And here, you go from left to right, wavelength increases. Inverse proportion. And again, you need to understand this. Towards the left side of the spectrum, higher frequency, higher energy, shorter wavelength. Towards the right side of the spectrum, lower frequency, lower energy, higher wavelength. Understand that? So frequency and energy have a proportional, or they're in proportion. Both increase, wavelength decreases. And then we see here that wavelength and energy are inverse. Cool? Understand that, everyone? Understand that? Cool. Okay. This is where it gets difficult. This is the tough stuff here. I can't pronounce it, but it's quantization or something like that, whatever. Yeah. So electrons associated with atoms. So the electrons, when we have our electrons in atoms, they're associated with quantized energy levels. And we usually have absorption, which we'll talk about, or emission of energy is associated with the movement of electrons between energy levels. And these, when we look at our chart here, these are energy levels. So when atoms move, whether it's through absorption or emission, they're associated with the movement of electrons. So something that's being absorbed or emitted is basically the movement of electrons. And we're going to talk about absorption and emission soon. Planck, he proposed the theory of quantization, and basically he said that energy is quantized. And what he means by quantized is that energy can only occur in certain distinct amounts. So you guys are going to see on your activity today, they're going to give you a model of hydrogen, and you need to understand that hydrogen has certain energy levels, and that's what they mean by quantization. So I gave you guys an example here. These are 4 energy levels, or 4 types of energy. These are certain energy. This is not like, these are just made up numbers, but for that specific element, these are the quantized energy levels. Certain energy levels. Cool? And then he further proposed an equation where he related energy with frequency, and that's how we know they're corresponding. When energy increases, frequency increases. And he also developed the Planck's constant, which is H, and is denoted as 6.626 times 10 to the negative 34 joules per second. Cool? Then the last 2 things you need to know for this activity is that Planck, and it's on your activity, he further proposed, or he related wavelength of light to the energy of light. So energy and wavelength are related. So if you guys look at question number, on page 78, question C, they ask you what mathematical equation relates the wavelength of light to energy of light. I gave you guys the equation right there. Energy is equal to Planck's constant times the speed of light over wavelength. So that is the equation that relates the wavelength of light to the energy of light. And notice you have 2 constants, Planck's constant and the speed of light. So they tell you to calculate something, this is it, calculating energy. They already gave you guys the wavelength, and they gave you the 2 constants. But note that the wavelength is in nanometers, wavelength has to be denoted in meters. So just giving you guys the hint. Most students fall for that, I didn't want you guys to fall for that. So, cool? And here it is, the most complicated part of the activity. Please, if you guys can, pay attention to this one, because I don't know why, but everyone has a hard time. This is the hardest stuff, okay? So this is Bohr's model, and it's not that hard, but it's just, I don't know, I guess you guys have, or Gen Chem 1 students have a hard time. Not you guys, but my first 2 classes. So this is the Bohr's model, okay? This, again, is talking about emission or absorption of energy. Relating this to the spectrum is just hardcore. You guys are going to learn this in physics. Cool? So you guys notice here, this is specific for hydrogen. There's 6 energy levels in hydrogen. Okay? N equals 1, N equals 2, N equals 3, 4, 5, 6. Cool? When, yeah, hold on, we'll get to that. So we see here, electrons in the hydrogen atom can only exist in specific energy levels. Quantization. What does that mean? Specific energy. You guys will be given these values. Specific energy. If you see energy outside of this, it's not true for hydrogen. It could be for another element. Cool? So when a hydrogen atom, or when any atom is heated, its electrons in the ground state absorbs energy and can be excited to one of a higher energy. So the first thing you guys need to know is the lowest level, N equals 1, is in its ground state. When we heat up an electron in an atom, or an atom in an element, I meant. When we heat up atoms, they go from the ground state to an excited state. So we say that they got excited. They're happy. They're going to a higher level, okay? So when an atom is heated, it will go from its ground state to the higher state. It will not emit energy. It will absorb energy. Cool? You guys need to know that. You guys are going to notice here I put these different types of light, but this is being absorbed. So if you guys look at white, this is being heated. We're heating up that hydrogen atom, and it's going from the ground state to an excited state. It doesn't matter what energy level. It could go up to n equals 6 or n equals 5 or even n equals 2, okay? This is what's important. Once electrons are in this excited state or higher state, they can release energy. And when they release energy, they go to a lower state. They will go from like n equals 4 to n equals 2 or n equals 4 to n equals 3. And when they release energy, it will be in the form of light. So for the hydrogen, for the Bohr's model of hydrogen, you will see in n equals 1, the ground state, when something is being released, if it's going from a higher state to n equals 1, it will release light or release energy in the form of light. Okay? If something is being emitted, or it's going from a higher state to a lower state, and it goes to n equals 2, visible light. That's the only light you can see. And there's going to be a trick question on your activity. It's going to say, based off what you're seeing with light, does this agree with Bohr's model? No, because you do not see UV light or IR light, cool, or infrared. So if something is being emitted from the n equals 6 or n equals 5 to n equals 3, it is releasing energy in the form of IR. Okay?
So we don't see it.
You don't see that either. You only see up to n equals 2. Okay? Now something else that's really tricky, and not as tricky, but you guys need to understand because I ask you guys constantly in this. All of this, when it's moving, remember when we talked about it, the absorption or emission of energy is associated with wavelength and movement. Everything is in wavelength here, okay? What did Bohr took this from Planck. What did he say? He said as wavelength decreases, energy increases. So they ask you guys, and I don't know why people kept falling for this. If you see something that goes from n equals 6 to n equals 1, or something from n equals 3 to n equals 2, which one would emit more energy or light? N equals 6 to n equals 1 or n equals 3 to n equals 2? N equals 3 to n equals 2. Again, you see you fell for it. As wavelength increases, energy decreases. This is in wavelength. So n equals 3 to n equals 2 has the shortest wavelength, it would have the most energy. And that again relates to the spectrum. So I don't know why, I was grading papers yesterday, everyone fell for that. Most people got that question wrong. Please do not fall for that, guys. You guys are my 3rd class. Make me happy. I don't know why they don't pay attention, I guess, but I'm saying it again. Shortest wavelength, highest energy. Don't fall for that, because they say if they get that wrong, that's -1. Most of them got to be on that activity for a stupid mistake. Cool? Understand that? Capiche? Everyone got that? Great. Awesome.